Greetings and welcome to, the program, another installment of Quantities. This is 10 in our basic application series. This time around part 4 of our mini-series on continuous quantities. If you have not yet already, I would suggest you check out the first 3 videos in this mini-series. You can also check out the channel About page for information about ready-made playlists. In our action-packed previous edition, we left off with the question of how to visually convey the relationship between a continuous random variable and the probabilities associated with its domain. Because the domain of values a continuous quantity may take is infinite, it should be fairly intuitive that enumerating values using either a table or line plot, as we've done in the past with variables or quantities with a discrete and finite domain, simply doesn't make sense here. If you will, allow me to introduce you to the so-called probability density function, or PDF for short. We're going to take a look at a couple examples here, but we're going to start with the uniform distribution. If X is a uniformly distributed random variable, then we can show its PDF thusly. There's obviously a lot going on in this plot here, but before we break things down and work with this a little bit, let's take a look at an equivalent representation using mathematical symbology. You will recall way back when in our foundational series during our discussion on math terminology and symbols, I mentioned that using symbols can make expressing things more compact and concise. Here we go. This is quite an example of that. We're expressing the same function we were just looking at graphically using symbols. What we're saying here is that the density function returns a value of 1 if the random variable is between 0 and 1 inclusively. Otherwise, it returns a value of 0. So let's go back to the graph here. How do we use this plot, or this graph, to find probabilities associated with the values of our random variable? The key to this is that unlike with discrete quantities, we do not actually map domain values to probabilities. Rather, we map regions or ranges of values of our random variable to probability. The probability is the area or volume of the function cropped at the region or range of values of our random variable. So for example, the probability that X is, say, greater than 1/2 is equal to the area of the shaded region here that we have on the plot. I deliberately chose to start with the uniform distribution to make things easy to deal with because calculating this area is pretty straightforward. The shaded region is a rectangle with a height of 1, you can see that, and a width of 1/2. The area of this rectangle is therefore 1/2. And hence, the probability that a random variable uniformly distributed over the unit interval is greater than 1/2 is 1/2. One more, just for practice. What's the probability our random variable will be between 0.4 and 0.6, or 2/5 and 3/5, if you like ratios? So here, in the similar spirit, we have a region that's a rectangle. This rectangle has a height of 1, just like in the previous example. This rectangle has a width of 1/5, so its area is 1/5. The probability our random variable is between 0.4 and 0.6 is therefore 1/5. Not too bad. So I think you know where we're headed here. The Gaussian or normal distribution. And what we're looking at here is a path plot of a standard normal probability density function. And I should point out that the term standard normal has historically had a couple different interpretations, but nowadays the term standard normal refers to this distribution here. Standard, as like an adjective, refers to a particular way of centering and scaling this distribution, the normal distribution. So what does that mean? Notice here that the peak, also called the mode of the function, is over 0, directly over 0. And one more thing, the area, for example, between -2 and 2 is a particular number that happens to be a little bit over 0.95. Equivalently, the standard normal PDF is a normal PDF whose mean or expectation or average is 0 and whose standard deviation is 1. Note that the tails of the Gaussian distribution keep going. So the one tail on the left here runs towards negative infinity and the one on the right towards positive infinity. However, as we move farther away from the mode or mean, the region of these tails becomes extremely fine. And to give a sense of this, the probability that our standard normal random variable is greater than 5, which is sort of to the right outside of the plot, is about 3 over 10 million. So it's a very fine slice. We always need to be careful when we use words like always and never. We can, using the power of mathematics and a lot of unnecessary toilsome work, create counterexamples to these two assertions here, but the counterexamples would be way out of usual convention, like showing up to a funeral dressed as a clown or something. I guess if the funeral was for a clown, dressing up as a clown to go to the service or funeral or might even be required. I don't have the answer to that one, but in any case, so we can pretty much hang our hat on these two statements here. The value returned by a probability density function will not be negative. That's the first statement. And the total area of the PDF equals 1. That's the second statement here. On the bottom equation, the second statement, the symbol that looks like a lazy S here is called the integral symbol. This is the first time we're seeing this here on QuantSlob. If you will recall from part 2 of this mini-series, I mentioned that with continuous distributions, we need to manage infinity. And this is basically what I was talking about. Integration is a powerful tool we can use to generally find the area of a function. If you're not familiar with integration, at this point you probably shouldn't worry about it. Suffice that it's, like we said, it's a technique for finding the area of a function. It's great to know calculus, but practically speaking, we can use software to calculate our probabilities, and there are other resources we can use too. If you are familiar with integration, you might be wondering or thinking to yourself, aren't these measures here usually defined for the real numbers? And the answer is yes, they are, which is precisely why we took a peek at integers and rational numbers in part 2 of this mini-series, although perhaps not for the reason one might think. So we have some loose ends to tie up here. Don't miss our mini-series finale, part 5. And that's it. That's going to do it this time around. Thank you very much for tuning in, and don't forget to stay tuned for more QuantSlob.